Okay, limits in calculus. Several different types of limit problems that you'll see in calculus. I'm talking about the AP exam, and so this film is meant to bring those to light, and hopefully you can distinguish from one limit to the other about what plan of attack you will have to evaluate said limit. So there's really 7 different types of limits that you'll face, limit challenges that you'll see on the AP exam, and we'll move through these quickly and give you an example of each. So this part 1 has 4 examples on it, the first one of which will be top-bottom limit, where you have to factor, cancel, and then substitute the limiting value. The second type will be that of the definition of derivative. The third example will be a fraction that will have the same degree on both top and bottom, and we'll have to evaluate that limit. The next type of limit will be function racing, kind of horse racing. Which type of function races to infinity the fastest? And on part 2 of this video, we'll look at the L'Hopital's rule along with graphing in order to evaluate the limit. And lastly, the squeeze theorem, kind of the new kid on the block in Calculus AB that you'll have to know how to execute and realize that you need to use the squeeze theorem in particular cases. All right, so here's the first type. Here comes 4 examples for you. We want to, this is the factor, cancel, and substitute type of problem. We're evaluating the limit as x approaches 2 of x squared plus x minus 6 all over x squared minus 4. We can see immediately if I attempt to directly substitute in the value, I got a problem on the bottom because I'm going 2 squared on the bottom is 4 and 4 minus 4 is 0. I can't divide by 0, so I got to figure out how to get rid of that problem child. And the solution, of course, is to factor both the top. So x squared plus x minus 6 factors into x plus 3 times x minus 2. Factor the bottom into conjugates. There's a difference of binomials, 2 perfect square binomials. Factor that into x plus 2 times x minus 2. Now you see that top-bottom relationship of the x minus 2s are history, and that leaves us with evaluating what is remaining. So wherever I see an x, I plug in the limiting value of 2, and I get the answer of 5/4. So got to be able to recognize a factor, cancel, and substitute scenario like that one. You're not going to get on the AP exam some limit scenario where you simply plug in the x value, snap your fingers, and get the answer. They're not going to be that easy. So you're going to have to resort to one of these strategies, techniques for solving. So factor, cancel, and sub is one of them. Here's the second, and it's the definition of derivative. So sometimes you see a problem and you got to have bells go off in your head. You see this problem like the limit as h goes to 0 of e raised to the 2 plus h minus e squared all over h. Well, what needs to occur to you, and you kind of have to have bells going off in your head when you see an expression like this, is that this parallels the definition of derivative. That is the limit as h goes to 0 of f at x plus h minus f at x all over h. Now, the warning here is, and students make this mistake, they spend a whole lot of time trying to evaluate this limit by putting in smaller and smaller values for h. Do not attempt to put in smaller and smaller values for h. Even if you're in the calculator portion, putting smaller and smaller values for h in your calculator is going to do you no good. What you need to do in order to evaluate this limit is to first determine, steal from that complex definition of derivative notation, what the function f of x is. In this case, I realize that f of x is equal to e to the x. And so now I got to take that derivative. Well, the derivative of e to the x is real simple. That's also e to the x. And then they put a value in for x so I can evaluate this limit at the limiting value. And it's not 0. I'm actually putting a 2 in for x. So what I get here is f prime at 2. Wherever I see an x, I plug in a 2. I get e squared. The limit as h goes to 0 of e to the 2 plus h minus e squared all over h is really, in disguise, the function f of x. And I'm getting closer and closer to the value of 2, infinitesimally close to where those 2 points kind of merge together into 1. And the slope of the tangent line of the curve e to the x at x value 2 will be e squared. That's what you have found. So you got to recognize a definition of derivative symbolically, then steal f of x from that definition. Figure out f prime of x just using your derivative shortcuts, and evaluate f prime at whatever values provided. And again, the students I've seen spend a lot of time on this and get nowhere and miss the problem. They're attempting to plug in smaller and smaller values for h to no avail. Don't let this happen to you. Third example. You got the same degree on top and bottom. All right, so oftentimes we try to figure out which function, the top or the bottom, is headed to infinity the fastest. Well, the truth is here, don't be confused. On the top, I have a second degree expression. And on the bottom, I also have a second degree expression when I rewrite this thing in degree descending order. So I think the real key here is, can you write both the top and the bottom in degree descending order? So the problem now looks like this. The limit as x goes to infinity of 3x squared minus x all over negative 4x squared plus 7. Well, the dominating term on the top is the 3x squared. The minus 5 is insignificant when I approach infinity. The dominating term downstairs is negative 4x squared. The plus 7 doesn't mean jack as I get closer to infinity. So the truth is I have a tie game with regard to degree on the top and bottom. When that happens, all I do is I steal the leading coefficients to find my limiting value. And we find here that as x approaches infinity, the limit of this expression is negative 3/4. So you got a tie game, top and bottom. Make sure you reorder in degree descending order, both the top and the bottom. Pretty easy to simply take that ratio of leading coefficients and arrive at your limiting value. Here comes number 4. This is function racing to infinity. And there are some students that haven't caught on to this. So different types of functions you should be familiar with, right? You have a natural log function. You have a linear function. You have a power function. You have exponential functions. And all those kind of travel to infinity at different paces. Especially as we get close to infinity, one of those types of functions will dominate the other. So different types of functions travel to infinity faster than others and dominate in comparison. Check this little diagram out. We've got red, yellow, and green arrows, kind of like a stoplight. We've got slow stuff on the left and functions that travel to infinity very quickly on the right. So here's kind of the list of pertinent functions you need to know from slowest to fastest. We go log x, then natural log x, then linear. You can see a line kind of crawls to infinity. As x goes to infinity, the line goes to infinity as well. The positive line will, just not all that quickly. Picture that against a power function like x squared. Well, as x goes to infinity, x squared is going to soar past the linear function. X squared, a power function is x cubed. A power function is x to the 5th. A power function is even x to the 82nd power. That's a power function. Yet there's still one function that will dominate the power function no matter how high that power is. It's kind of difficult to convince yourself of this. But an exponential function is the fastest growing function as x goes to infinity. We can always recognize an exponential function when the x is in the exponent, like 2 to the x power or e to the x power. That's a whole lot different than x squared, where x is in the base. Again, when the x is in the exponent, that's how we recognize an exponential function. So knowing that, here's an example of some function horse racing we have going on here. we have the limit as x goes to infinity of x to the 99th power. What type of function is that? X to the 99th is a power function. Over e to the x. Well, the x is in the exponent. We recognize that as an exponential function. So as x gets very large, and this doesn't happen quickly. This doesn't happen anywhere near 0. E to the x will take some time before it dominates x to the 99th. But it will as x goes to infinity, as x grows very large. So what I need to understand here is that the top is a power function, and the bottom is an exponential function. And when I compare these two, as x goes to infinity, the power function grows to infinity relatively slow. In comparison to exponential, it goes to infinity relatively slow, while the exponential function goes to infinity very, very fast. So you can picture this as a relatively small number over a huge number. And when that happens, of course, you're going to get a limiting value equal to 0. So when you get the different types of functions on top and bottom, you've got to know which horse races to infinity the fastest and compare the top and bottom as such. So those are the first 4 examples we have for you. 3 more examples coming of different types of functions that we will visit here in film number 2. Limits on the AP exam. More to come. Over and out.